Now, for homework of section 5.5 is on page 505. Please do problems 253, 55, 57, 61, 63, 65, 67, 71, 75, 77, 81, 97, and 309. And when you're finished with the homework, please come back and I want to talk about 3 of them. So now that you are done with the homework, let's look at problem 253. Now the problem asks that if the series converges, whether it converges conditionally or absolutely. Now first let's consider the absolute convergence. If you compare to the absolute value of the series, okay, it's positive anyway, so it doesn't make any difference. Well, compare it with this series right here. That is square root of the n over n, because this one is just have the only difference is +3, and when n is huge, like a trillion, the 3 doesn't make any difference. So then, as a result, if you compare to that series, then you realize that it equals to the comparison test. It goes to equals to 1, which means that this series and the other one, this is a p series, and converge and diverge at the same spot. And being that the p is less than 1, it's just 1/2, and therefore this series diverges. If you slap on the absolute value, which means that that the convergent, it doesn't converge absolutely. Well, does it converge conditionally? So then we follow the alternative test, okay, which says that first the limit of Bn has to go to 0, right? So we did a similar thing as the absolute convergence. We calculate the limit, which is just the same as 1 over n squared, right? And then that similar to this one. So then it does equal to 0. And then the next question is Bn plus 1 bigger than Bn? So I wrote down Bn plus 1 and Bn there. And how would you prove that 1's bigger? By the look of it, it's not that obvious if one is bigger than the other. So you have to, do grunt work. You do the subtraction, and then you do that radical sign trick where you multiply by the positive term or something, or multiply by something. Well, yeah. Anyway, you do something, okay? You manipulate the algebra until you come up with something like this. And this, well, the other side, do the subtraction or multiplication. I don't even, why do I have, maybe I should have been multiplying instead of subtracting. Doesn't matter. The point is, you end up having something that's subtracting is going to be less than 0. It's reasonable to believe that it's less than 0. And for n bigger than 0, and especially n is going to infinity. And therefore, the Bn plus 1 is bigger than Bn to satisfy the alternate series test, and therefore the alternate series does converge. It just doesn't converge absolutely. Next, let's look at problem 263, which is actually easier than the previous one we did. In this case, the Bn being bigger, that is Bn plus 1 is bigger than Bn. Bn is bigger than Bn plus 1. It's decreasing, right? So Bn is bigger than Bn plus 1. That's quite obvious because n is only under a fraction, one fraction, instead of being stuck in a bunch of them like before. Oh, I forgot to mention that I changed the solution before. The n times n plus 1 should be multiplied on this side because of this. I don't even know why I wrote it as dividing, but it doesn't change anything because all we care, because n and n plus 1 is positive, and all we care about is proving this thing is less than 0. But anyway, getting back to here, we prove the first condition, which is Bn is bigger than Bn plus 1, okay, for obvious reasons. And then as n goes to infinity, the Bn goes to natural log of 1, which is 0. So that's also obvious. So this converges by the alternate series test. What about the absolute convergence, which means if we ignore all the plus and minus signs? For the absolute convergence, we can rewrite this thing in the telescoping series. where you have each term subtract something out so that you got only the first term and the last term left, which is natural log of k plus 1, and that of course goes to infinity slowly, but it does go to infinity, so therefore it doesn't converge absolutely. The last problem we'll talk about is 265, where we have the sum of a neat looking thing that, well, tolerably neat looking, where you have n to the power e on top and n to the power pi on the bottom, and you have 1 plus there and so on. Now this series, as n becomes large, will approach 1 over n to the power pi minus e, because there's a 1 down here. Okay, the only difference, there's a 1 down here, but it's just 1 when n becomes a trillion. That 1 isn't interesting at all. So then we have, so the series can be, what is this? Limit comparison test, I guess, or just comparison. I don't remember which one. The point is, this series can be compared to the other one, and this is a p series, and the p series has a value of p where pi minus e. Did I write pi equal to e here? I mean minus. Okay, so pi minus e is equal to 0.42. And that's less than 1, so the p series diverges, and this series does not converge absolutely. So if you ignore the negative sign, it's not going to converge. And so therefore, our next question is, does this series converge by the alternate series test, conditionally, that is? Well, we can see that the Bn does go to 0 as n goes to infinity, but the first condition is, is Bn plus 1 less than Bn. Okay, that's well, if you write it out, it's not that obvious really, but maybe the book just wants you to say, well, it's a decreasing function, you know, of course Bn plus 1 is less than Bn, it's getting smaller, so we'll just call it decreasing, which is which is okay, I guess. Or if you're real picky about it, to prove beyond a doubt that Bn is plus 1 is going to be less than Bn, then we can do this. Okay, do it the brute force way, which is you let function of f of x equal to that stuff and take the derivative. And I even wrote down that there's a derivative calculator. I wrote down the link on the page, so you can skip this mess of differentiation if you want. But eventually, even with the calculator, you have to come up with this. So eventually what you get is this thing for x is where x is positive. Now, as you notice, in this mess, eventually you get to stuff is being added until you get e minus pi in there. Okay, I've double checked this with a differentiation calculator, derivative calculator, I mean, and then and this is correct. So I didn't mess up in this mess. I mean, it's so easy to mess up, right? I think I did mess up, but did catch myself messing up or something. Anyway, I got here. This is correct. And as you can see, in this whole situation has a e minus pi in there. And that, everything else is positive, but the e minus pi, as x goes to infinity, is going to multiply this part. Okay, that's just e, that's just a number sitting there. So as x goes to infinity, this negative number is going to take over the sign. That is, everything will turn negative. Therefore, the derivative is less than 0, which means the function is decreasing. And that is just the absolute proof of Bn plus 1 is going to be less than Bn for all large numbers of n. And that's, I don't know that the book necessarily expect you to go through all that, but that's just a surefire way of showing that the alternate series test does work. And that marks the end of this section.